So one of the ways we cut costs is we just completely, looked at a different set of components. I do believe that most people building robots today will admit that they learned in college how to build robots from professors who wrote the curriculum before the iPhone existed. The iPhone only came out in 2007. So,
June 29th.
So for those of you who went to school since 2007, it's a different story. But most people in the field, got their college degree before then. And so that's one way of building robots, is with LiDAR and with Intel chips and NVIDIA discrete GPUs and metal. And that's what you learned, and that's what works, and that's what's out there in the field today. And I believe that we're at this moment of change where we're going to see the next generation of robot builders inspired by consumer electronics. And they're going to build more things like smartphones on wheels. And so it's a very different set of components, which requires very different software, which is why the TickTock stack was very custom. But this is what's going to really bring the cost down. The depth sensor on the back of this phone is from PMD-Tech. Infineon makes the chip, PMD-Tech makes the sensor module. Those you could get for $150 dev kits, but you really couldn't get them in volume at low prices. But because they made tens of thousands of these phones, you can actually get them for about 20 bucks with some sizable volume. So a $20 full frame time of flight depth sensor is possible because of augmented reality. A quad core 2.6 gigahertz chip with neural net accelerated hardware that does all the feature extraction of the computer vision SLAM system in hardware acceleration is about 20 bucks if you get the all-winner version, or 65 if you get the Qualcomm version. And again, this is possible because of the investments being made in mobile. Versus most robots out there are using an $800 to $1,000 hardened Intel box. And so it's just very different price model from the old way of building robots to the new way. Again, this was with the electric skateboard. So since I couldn't show you all of the features,
I'll give you a quick update on our software.
Let's give you a video.
In progress. What you see over there is just a Kabuki robot with the phone on top running our full stack robotics suite running on top of Android. What we see here is a map. We can see the purple indicating the location of the robot on the map. And we've got a video feed that works whether you're on local Wi-Fi or remote, and a joystick to tele out the robot. But as we know, driving robots is best for RC cars and toys. What we really want is autonomy. So we've given the ability to define destinations for the robot, and it will automatically plot itself a course to go there. And while that 2D app is really cool and familiar for most people, the wave of spatial computing through ARKit and ARCore is an even more interesting way to interact with the robot. So what we have here is our augmented reality controller, where I can just tap a destination on the ground, and that becomes a new goal for the robot to travel to, which you can see in the green route that it's planning. We can give multiple destinations, sort of like leaving breadcrumb trails for the robot to travel over. And we can see one at a time. It will plot itself a course to get there, going to each goal, and then plotting to the next goal. Augmented reality is also a great way to set up the map. So let's say we want to add a new point of interest over here. Garbage can. All right, now we have a new spot on the map called Garbage Can. And we can say, okay, Google, ask TickTock to go to the garbage can.
All right, getting TickTock. The robot Gus is going to the garbage can.
And of course, we can use voice right on the augmented reality app as well. Go to conference room. So there you have it. That's kind of the highlights. We've got the autonomy suite, the new navigation system, mapping, augmented reality, 2D control, all running on top of Android on low-cost chips.
Sorry, couldn't give the live demo. You have to make a good base map for that stuff to work. And I think the map we tried today was not so hot. We were rushed. But those are all of the features. And so I believe that there's the spectrum of HRI. That's the human-robot interaction. And in computers, you call it HCI. So on one end, you have voice. It's super low friction. You just, when the Echo launched, people questioned, why do I need the Echo? Everything the Echo does, I can do on my phone, I can do on my computer. But all it did was remove the friction to doing those actions. You just open your mouth and start talking, and that turned out to be really valuable. So that's how you're going to command the robot in most cases. But voice is very low bandwidth. It's not full duplex. You can talk, and you have to shut up and wait for it to talk back. It's a very low bandwidth stream, and it's very low precision. So you move forward to like a 2D app, and now I can touch and pinch and zoom, and I can read a whole bunch of information. I can talk to it, it can make sounds back, and so that's a pretty good compromise. On the other end is augmented reality. There's more friction. You've got to pull out your phone, it's got to localize where you are in space, you have to launch that app, so that takes longer to do. You're not going to do that frequently. But now you have a super high bandwidth communication between you and the machine. You can pinch and zoom. You can move the phone in 6 degrees of freedom. It can, in 3D, show you what the world it sees looks like. It can pre-visualize the actions it's going to take for you to okay them. It's this phenomenal, dense way to connect to another system is through a mobile device. The next step after that would probably be some brain implant. So there needs to be this spectrum. This is the basics of why AR really matters. So what you see there on the left is a screenshot from the phone that's mounted to the robot. It sees me standing there and a bunch of yellow features in the world and the map below it of how it sees where it is relative to all of those features. And then on the right is a screenshot from the phone, how it saw the opposite view of the world and all the yellow dots and the features that it saw and where it was in the map. So now we have a phone and a robot that are talking on the same coordinate frame. And so X, Y, and Z data means the same thing to both devices. And that's what makes this possible. This is what won't be possible with a LiDAR-based robot. No matter how cheap LiDARs get, if the robot sees the world in a 2D plane and your phone has a 180-degree view RGB camera, you're just not talking about the world the same way. It's very hard to have that interface with that. In terms of some of the things that we built, Tony, after this talk, please ping him to ask a lot more about some of the path planning, but we had a very simple A-star implementation of planning the big global planner, but we did have a unique multi-layer map. So the map was represented with, we had a base map, we had the ideal trajectory, it was basically represented as a cost map, and the idea is everywhere the robot traveled would be a known safe space that would reduce the cost of traveling in that area. Every time it collided with something, that would be marked in the map as a high cost area, likely to have obstacles. And over time, you would build up this really good map where it would know where the safe places were and where the risky places were, and it would adjust its velocity based on the cost for that spot in the grid. So if it was in a dangerous area, it would go a little slower. If it's in big, wide open space with low cost, it would go faster. We added some obstacle avoidance. That is fusing color and depth. With color information, it's easy to get false positives. Patterns in carpets might look like an obstacle. And with depth sensors being noisy and imperfect, it's easy to get false positives or false negatives there. You don't really see a Cheerio really, really well in the depth sensor. You do see it in RGB, but it could just be a dot in the carpet. So one of the first things we built was a Cheerio not Cheerio detector, fusing color and depth. And one of our vacuuming demos is it would go vacuum up the Cheerios and it would avoid the Legos. And so that's the idea of hybridizing those. The third box is something we did not implement. So our planner was based on a trajectory rollout type design that I believe Fetch and other cylindrical robots use. It's very good if you just have a cylinder robot and you're just planning your path based on the center of the robot. If you have something elongated, like that hot dog shaped robot there, or if you're towing something, it's a much more complex operation to plan how do I get through an opening with my funky shaped robot or non-diff drive robot. That's where you would need a different planner that we did not implement. And that's where I think machine learning would actually start to come in, because that's a screenshot from something called timed elastic bands, which is awesome. I think Locus or Six River Systems uses it. And it's really fantastic, but there's like 30 knobs you have to tune for how the robot's going to drive. So every time you go do a deployment, you got to bring a stack of interns to sit for a week and tune the thing. And if you're manually tuning something, that says you should be using ML. The thing on the right is a screenshot from a thing from MIT that we also didn't implement but wanted to, which is socially aware navigation. So it's recognizing obstacles by what they are and what activity they're doing and planning its route based on that. This would have been really important in a grocery store. So this knows to not run right behind somebody because they might step back and not see you. So behind somebody you need to give them more space. In front of them you might be able to give them less space. So these types of things are where machine learning is really going to be important in robot systems. I'm going to skip through this, and so that is it for my talk. I'll take a few questions. Go ahead.
What are you using for voice recognition?
So we were using both Alexa and the Google Assistant. And
You've got to have connectivity to. Yeah.
So the shipping robot would have had onboard voice recognition for the basics of, go to destination B. And it would have destination B locally, and it would be able to interpret that. For all of our demos, we did use cloud systems of both Alexa and Google. Yes?
In the retail space, did you look at scanning for outs, for restocking?
What was that, scanning?
Scanning for empty shelves.
So the question is, did we look for like inventory solutions on top of the retail robot? I think that would have been a next addition. There's a bunch of folks in that space. Cindy, Bossa Nova fellow are in that space. I think they're all doing a pretty good job at that. There is some question about whether those things need to be robots or whether they should be a sensor box added to shopping carts, or whether sensors are getting so cheap, aisles should just be outfitted with sensors everywhere. So we really wanted to focus on something that had to be a robot because it had to move physical goods. There was no other way to solve it. But I think that would have been a nice accessory, absolutely. And one of our loves of using Android as robot OS is we're just a USB port and an APK away from supporting any accessory. We wouldn't even need to write it. So somebody like Target could write a barcode reader app, or they could have some other accessory app that interface with their employees or with their customers, and they would just affix the sensor, plug it in over USB, deploy the Android APK to the robot, and it's up and running. Question in the back.
So what would be the average price for like an average consumer who wants something very similar to this in their own home?
So we felt the TidyBot, we would have had a bill of materials under $200. That's just the mobile basket. It would have been up a bit higher if we were adding some vacuuming utility to it. For the tall tower, I think there's, not counting the expensive 3D printing, and by the way, I don't mind sharing, that cost $9,000 to have printed in nylon. There's a lot of labor, there were a lot of parts, there was a lot of prep work and post work, but Fathom does really good work. Other than that, it's only $1,500 worth of parts in there in unit quantities of one. In higher unit quantities, we think we could have built a similar tower for about $750.
Would you ever make like a modular set for a household? So like you buy whatever you believe that you need for your home at first, or you go out and buy modules that actually need.
Yeah, so the question is about modularity for the home. So our original slider concept was really all about modularity. And it was saying the compute and the sensing, the batteries, actually a LiPo battery is a big part of the cost, and the motors, that's where the expense was going to be. And then the utility of whatever function it did was probably more modest in cost and could be varied in cost, and so that would be an add-on.
What's the payload of the white tower? Base?
This particular unit is super fragile. So
Well, I mean,
we babied
that
it.
base that you mentioned before, that on the bottom there, what's the payload?
We were targeting 200 pounds. So the item that the product that we would have made and taken to production would have carried 200 pounds. This 3D printed nylon one with super glue holding it together is our fragile, like, CES show car. We treat it carefully. Let me take a couple more questions because we've run a bit long. Go ahead.
You held up a phone and said this is the very last one that'll ever be designed with these depth sensors or something. But surely this is not really going away. What's replacing it?
So the truth is that Apple sets the trend for mobile devices. And so Lenovo, Asus, and others have all had opportunities to make Tango devices, and carriers have to promote them and sell them. And for just a variety of reasons, it was not taking off, adding the depth sensor to it. It not only impacts cost, but it impacts the battery life, it impacts the form factor, the design, the Z height. So there were just a lot of excuses that OEMs would make to not adopt this at large scale. So we might just be one killer app away from depth sensors coming back to the back of mobile devices. Whether that starts from an Android device or from an iOS device, nobody knows. But
Can you still buy those?
You can still buy these, and they're relatively inexpensive. So you can get brand new ones still.
Sadly, they suck as phones. Like, you don't want to have them as your personal phone, so they're getting eBayed more and more.
It is my personal phone, but sure. But no, you can buy them, and the Tango APIs, while it's been deprecated, you can still hack them. I think you had your hand up earlier.
Yeah, thank you. So you mentioned that the mapping is the most critical aspect of all of this, and at the same time you also mentioned about multiple interns working there. If you had to deploy a product overnight to a new customer in a big warehouse, have you solved the problem of mapping not as in a sequential case from a single device, but multiple drones running around and then putting the map together?
Yes. So I'm just going to have this muted, but our plan was to use VPS from Google, which you see here. This is a TechCrunch little highlight of VPS, which was announced at Google I/O in 2017. It stands for Visual Positioning System. And it's cloud hosted by Google, multi-agent, lifelong mapping. And the idea is, Google will go out with operations teams and map the world, and robots can then run on those maps. You could make the maps with robots, you could make them with handheld devices. There's many different ways to make the maps. But a big map will exist, and then any device could localize against it. At this year's Google I/O, they showed it being used outdoor for walking navigation, and they announced something called cloud anchors, where two devices can share the same frame of reference shared through the cloud. And so our belief is that mapping is critical to a robot, and it's finally a solved problem for robot makers thanks to AR. It's solved enough. It's not solved in like nobody should work on it anymore. There's still lots of more robustness, changing lighting conditions, optimizations, but it's good enough to get to production, I feel, using Visual SLAM. Should we, who's running the clock here? Should we stop?
Yeah, should probably wrap it up. People can ask questions after.
All right. Well,
yeah.
Then that will be a wrap. I'll be up here if anyone wants to come up and ask questions.
Ryan, that concludes our meeting. Thanks to everybody for coming, and feel free to hang out and chat, ask questions to Ryan until 10 o'clock.
I forgot to mention one more quick thing.
HPRC challenge.
Next month, HPRC challenge.
Mailing list.
I forgot one more important thing. I mentioned that we didn't get funding for the consumer story, and then we pivoted to retail. I forgot to end with the fact that we did not get money for that either. And we've actually shut down operations of the company a month ago. So we're not actively pursuing this anymore. But I agreed to give this talk several months ago, and I said, look, I'll just still come give the talk, even though TickTock is not active anymore.